Thank you all for being here today. I'm super happy that we got center stage. It's a great hall. It's also a bit frightening to me. I didn't expect that. I thought I would be downstairs in the cellar and felt more comfortable with that. Anyhow, I've done what I've done, and I decided to introduce Rust to an angry crowd of Gophers without a back. Oh, there is a backdoor. That's good, but it's not going to be that bad, I suppose. So, who of you knows what Rust is? Has heard of Rust? That's quite a few. That's good. Usually, I find if I am supposed to compare these things while giving my own opinion, obviously, it's sometimes a bit bad to start with the thing you like more to be in front, and therefore I prepared this alternative version just to be sure that I try to remind myself to keep it balanced. Even though there are many things about Go that I think Rust solved better, it's also sometimes hard to decide what you want to like more or not. It's 45 minutes in total. It's a bit difficult to get through the first part in the given time, where I want to give you a little primer on Rust so that you understand what Rust is all about. Before I, in the second part, shall be a bit more practical. That's the actual comparison, where I try to go through the individual steps that are needed to do an actual project. Meaning, how do we set up a project, how do we test, benchmark, handle dependencies, deploy, and maybe even throw in some cross-platform compilation. Just because I like this so much. If you have ever done that, great, gorgeous. You won't ever miss that again. You don't ever want to miss that again, that is. And finally, there's some conclusion and maybe also some Q&A depending on whether we have the time or if there are any questions afterwards. We will see. First of all, let's get started. Let's get right into Rust. We just have 15 minutes. It's not enough to touch anything. I will rush through there. You will have many questions afterwards, and I probably won't answer them right away because time. But if you want to learn more, you should watch this video, Intro to the Rust Programming Language. Some of you might have done it. Alex Crichton, great guy, super smart, knows much more about this than I do, because I really just started Rust a few weeks ago. Rust, that isn't supposed to stutter. But it's a new language. This is the main page of rustlang.org. Rust about itself says, Rust is a systems programming language that runs blazingly fast, prevents almost all crashes, there's this big asterisk here, and eliminates data races. And because Rust is still alpha, it can do pretty much everything in the meanwhile, including eating your laundry. I think that's close to the truth, but not as bad after all. It sometimes makes you coffee if it feels like it. That's all the features here. Actually, I'm just highlighting this one because to me it's, whatever this is, who cares really? Because I want to show you what Rust is for me and why I think it's so great and what it has to bring to the table. Yeah, I've mentioned it many times, and I just want to be sure you understand that Rust is still alpha. We are talking about something very early, but we're also not talking about some ghost that is never going to appear. We're talking about these dates. They have been set in stone. These are going to be the dates for the beta, 31st of March 2015, and the 1.0 is scheduled for May 15th. So that's it. That's going to happen. We are talking about something that is going to happen very, very soon. It's also not done by just two guys or something. It's backed by Mozilla Corporation. So that said, let's have a look at why there is supposed to be, there it is, why there is supposed to be yet another programming language. Because we have everything, right? We also have Go, by the way. I don't know why it's not on here. I just blatantly copied this from Alex Crichton, and he didn't have Go on there. And maybe I should have put it in the spot of Java. But usually you have this kind of separation where you either have less control about how your memory is handled, but it's really hard to segfault or close to impossible. See interpreted languages like Python. Then we get kind of into the Java realm, which gets faster, and C++, that's the guys who are super easily segfaulted, and it's quite difficult to write good code. The more complex your program is, well, you know what I'm talking about. I'm not getting into details. C, C++ is kind of hard to get right. Rust doesn't even properly fit onto that line that was drawn there because it gives you kind of all the goodies without the baddies. That's how it seems. More control, more safety, and a speed that is close to C, C++. And it is already close. I can tell you that much. It's really efficient. And this is what makes Rust so attractive. This is what made Rust attractive to me. This is why I gave it a shot, especially when it turned 1.0 alpha. I was sitting on this thing and trying to learn it just so that I know that I'm not missing out on something great. And really is why I'm having this talk here. I just want to make sure nobody misses out on something that is that great. Or has the potential. So, Rust is safe. This is something they say as a first word here. Their features, Rust is safe, because that's their prime idea. That's the language that they want to create. They want to make sure that by default, you cannot have any memory-related issues or data races. And this is something they prove at compile time. This works through a very sophisticated type system that allows them to do proper analysis of what's going on in your program. This kind of analysis, a big part of that, actually a major part, if not the part, is the ownership tracking. So in this little example here, I'll just quickly go through this. We create a new integer, which is 5, on the heap, and then we pass it on to a helper function, which, if you look at it, just prints this thing out. And after that, we try to print it out as well. And in any sane programming language, I say, this would just be fine, because it is fine. It's read-only here, and nothing bad is about to happen. But the compiler will tell you something like that, actually exactly that. Use of moved value slot, okay? And then there's some yada, yada, yada. There is some... You know, usually you skip over this initially because you have no idea that this is actually a macro. And then it tells you slot moved here because it has type box U32, which is non-copyable. It moved this value slot over into this helper function, which now owns this value. So you cannot use it anymore after the call. Jesus. This is, I mean, come on. You can't do anything with a programming language like this. If something can ever be owned only by one guy, then you can't write programs anymore. But it's very safe. If you don't write programs, you definitely won't have any problems in these non-written programs. This is why they also have the notion of borrowing. This is the universal borrow operator. And I just made this up, but it's a borrow operator. What you see here is a new vector that we create, a mutable vector, by the way. And I'm taking reference to its first entry. So now this high variable should point to some string called hi, or that says hi. And now I'm trying to push onto that vector, whatever, which would definitely change the vector. And then I'm trying to print hi. So what do we get in that case? Let's see. Looks good to me, but Rust says no. Rust says cannot borrow v as mutable because it is also borrowed as immutable. So here it tells you that it can't do it, and then, oh, note, the previous borrow of v occurs here. The immutable borrow prevents subsequent moves or mutable borrows of v until the borrow ends. I mean, it's a long sentence, but it's plain English, and it is definitely the truth, because all it tries to tell you is that here you borrow indirectly v, because you take part of it as a reference, right? You take the first entry of v. And then you try to change it, which would put you into a position when you have one potential reader and one who can, in the same moment, write to it, which is a data race, if you think about it. Sure, not in this case, but it has the potential. So you can't write that in Rust. If you try that again, it's a bit small here, huh? But anyway, I can't change this anymore. If you try that again by just swapping the lines, first you do the write, and then you take the reference, then this will be just fine. There's another that's a major part of why Rust is safe. And really, that's all the trick that Rust has. It is able to track lifetimes, to track who uses what, when, in which context. But another great thing that I always wanted in a language and never got until now is the way it handles mutability. Because by default, everything is immutable. Yeah, it's kind of the inverse of what you know, right? So this code here, let v, we assign 1, and then we try to add 1 to it. This function here takes a mutable borrow to an integer, and then just adds 1 as it says. But let's see what happens if we try that. Okay, error, mismatched types. Values differ in mutability. So I'm trying to call add 1 with an immutable borrow, even though this guy wants a mutable borrow. Okay, so let's try to fix this. And what I do now is I say, okay, here you have a mutable borrow of v, right? And that's a very interesting thing that you see here, because not only in the signature of the function that you call, you have to say that you want to mutate that thing, but also when calling the function, you have to say it. So Rust code forces you to be extremely explicit about who reads and who writes stuff. And this is something new. You could say, yeah, it's verbose and I don't like it, but honestly, this is a game changer. But let's see what Rust has to say about that. Error cannot borrow immutable local variable v as mutable here. And here I'm always saying that would be great if the compiler would also tell you where the immutable local variable has been defined, which is right here. And as you can see, you know, things are immutable by default, so there's something missing here to allow that to be changed. So let mud v will now make this entire program work. It's quite incredible to see that, but this forces you to think about writability of your values and prevents or helps preventing races. The second big thing is that, sure, all the stuff that you've seen here before, it's not at the cost of performance, because all this is abstracted away. It is just a safety abstraction layer that goes away entirely when compiling this down to machine code. Also, there's no garbage collection, which can be a good thing if you want to have real-time applications. Also means you have to deal with heap allocated values yourself. You will have reference counted things. You will have something like smart pointers, and you can run into memory leaks due to cyclic references of reference counted things. So that's something you will have in that moment. Go is different in that case. You have generics. Generics, templates, however you want to call it. I prefer the term generics because it's kind of the more modern way of implementing this, which means that most of the thing you will have in or you will write in Rust will actually use these generics, which compiles down to the actual code as if you would have written it manually, which in turn makes sure that Rust is efficient. Sure, can blow up your file sizes, but doesn't have to. Sure, nowadays, you know, with all the cores that we have in our computers, a programming language has to make it easy to write concurrent code. Rust is no different. Therefore, you have everything you ever wanted to write concurrent code, and thanks to ownership tracking, it's easier than ever to prevent things like data races and these things. Sure, last but not least, it all compiles down to a single statically linked runtime that you can basically put anywhere. It will just work. This is an example for generics. I have to rush through this. I will not explain everything. So if you focus on this part here, I have two dogs. I've got a sizeless dog, which is a Chihuahua, and a bulldog, which can do any kind of sound. It's kind of any dog that I instantiate here. And we have two method calls here that make these dogs fight. And looks quite similar here because they all take an immutable borrow to the respective dog. But here, so that you've seen it once, is how you define a very, very simple generic function call, which can take any kind of barking thing that will be barking afterwards. So that's the kind of fast version because it compiles down to just one function that takes the actual types of these things and has no overhead that the polymorphic version has that will effectively do something like virtual function calls here. It's similar to C++ or to what Go does with interfaces. So just to see this once, that's kind of the equivalent of an interface, of a Go interface in Rust. That's how that looks like. Then, because we are in a Go meetup, that's how it looks like if you create a few channels and have a consumer thread that basically works on something he gets from the channel. Then you have another thread that produces some work and sends it through a channel. And finally, you have some sort of aggregator that will basically take all the results of the worker and basically just make sure that we get what we expect to get. This is, I'm just showing you this so that you see the difference, obvious difference, because Rust has all these extra features and kind of has a very different mindset about what it wants to achieve in this world. It's much more verbose, and the channel actually has two parts here. It has a read end and a write end, and there's much less syntactic sugar involved when you do certain concurrency patterns. But you have all the primitives that you need. So in Go, you have all the syntactic sugar around that makes it feel like it's very easy, but underneath is this stuff. And you have everything you have in Go. You have select, for instance, timers in Rust work just like the ones in Go. So you can have select statements that are handling timeouts and stuff really easily, very neatly. It's just a little bit more verbose compared to the respective Go version. And file sizes, binary sizes. Here we have working Hello World programs in the respective languages. And as you can see, what comes out of there, if I make a release build with Rust, 288 kilobytes of a binary that has just one dependency, which is the system lib on my Mac in this case. And the same program, the Hello World program in Go, comes in at 1.4 megabyte, but only if I specify these special LD flags that crunch it down for some reason. So it would be 1.8 if you just compile it like that. And yeah, this just out of the box how it is really slim, really small. And this, I think I will not talk about this too much, because you can have a look at the slides later on. It's just my attempt to show you what other differences there are, like native threads instead of having Go routines that in turn run on some threads. So there are plenty of implications that come with Rust, but in general you see that it is just a very different language. Now to the main part, which is actually the fun part. This was just a kind of dry primer, trying to rush through there to stay within the time limit here, 15 minutes, because I would like to have all the time for the main part of how it is to actually use this language and how it compares with Go. So initial setup. Initial setup is something that we actually do not even do in Rust, but before you do anything in Go, you will have to make sure you get the Go path straight. If you don't do this, things will just not work for you as you would expect. And this is really something that broke my neck when I started with Go. That's the first thing that I got wrong. Call me stupid, but yes, it's the first thing I got wrong. That's the first thing I get wrong when I get back to Go, and this will happen to me here as well. And I didn't plan this really, so you see lots of mistakes in the recording and stuff, but it's kind of natural. That's me doing this, and I didn't take like 10 takes on it, but just one. Also, just as a little technical note, I'm using TTY-Rec to record my bash sessions here, and Vim as an editor. I'm not a Vim guy. I suck at Vim. I can hardly type at all, and especially not in Vim. But I made it work somehow. Sometimes there are TTY-Rec related issues, so if things jump around, I will try to narrate over that and guide you through difficult passages. So now that we have the Go path set and are ready to go, we want to create a new binary, which is something like a Hello World program. How would that look like? On the left side here, we use cargo. Cargo is the universal tool that Rust developers use to do pretty much everything. You will see this a lot. So cargo new, I want to have a binary, I want this to be Git version controlled, I put into that folder, and that's pretty much it. So now I'm committing my stuff, and there we go. Fine, let's run it. Using cargo run, compiles it, does everything, hello world, fine. This is what you end up getting. These are the files that have been created, and everything below here is kind of the build stuff that it creates for you. Cargo clean kills all that extra stuff, and there we go. Cargo log file is something we will deal with later. So in the meanwhile, in the Go world, we have no cargo tool, kind of. We have Go, the Go tool, the Go program, which does a lot of work for us already, but it's on a lower level, definitely. So here we did everything ourselves and have a hello world program that I apparently do not, I ran it here, okay, fine. Now, let's get a library. The binary that we created is just, it's just a UI, front-end UI in terms of command line interface. In our case, if you want to do things right, you put all the functionality into an actual library. So we need to define that somehow. In the cargo world, we use the cargo toml file, which is kind of a manifest that holds all the information about our project. So here, that's kind of the default things that it created for me. And now I'm saying that I want to have a library that I put right here. So it's lib.rs. Names don't matter, really. And what I'm trying to implement here is a reverse function. It takes a string and produces a new string that is reversed. Seems quite simple. Should be done in a moment. Let's see. And yeah. This is kind of a constructed example because I wanted to make sure we have a bug to find later. I'm just pointing at the issues that we will have. So we are reversing the bytes directly, which is a problem because in every programming languages nowadays you have to deal with Unicode. Unicode is part of the business. Yeah. Here in the Rust world, I'm iterating bytes doing the same thing. What you can see is, okay. Here we have a type mismatch. So I'm trying to push a character which is a byte, but it expects me to push a character. A character is something like a rune in Go, which is totally Unicode-y. And what I'm doing now, which should tell me as a developer that I'm doing something wrong, I'm kind of forcefully converting my byte into a character, and Rust puts all kind of blockades into my way because all of these conversions can in fact go wrong, and Rust will always gently force you to handle your results, to handle your errors. So this seems to work now. Sure, some dead code warnings and stuff. You also see plenty of warnings related to I am alpha and you have to take special care of me. So you can just ignore that. Now on the Rust side, yeah. Oh yeah, let's go to the Go side. I'm too Rust heavy right now. In Go we have implemented the same thing, but I forgot to make the capital case thing work so that I can actually use that function because otherwise it wouldn't be exported. It's kind of a neat thing to think about. Here I ran into the same issue. Did I? Oh yeah, I ran into another issue, trying to use print line, but it expects the first thing to be a literal. And now let's see where we are. Here we are done, by the way. Go is kind of finished already, and here we are still trying to figure this out. Function reverse is private, okay. And this was this TDY rec hiccup. I just fixed the issue, but you didn't see any of this. All I need to do to make this private function public is to put a pub in front of it. So that's kind of the Rust version of making the first letter capital case. All right, every one of you will know that by now that we are working on bytes there, which is by default wrong when working with strings. And we want to try to find issues here. And thus we have to get into testing. How do we test? In Go, we have to write a separate file that is something underscore test, and then it will be basically picked up by Go test accordingly. In Rust, you can do that, but you don't have to. So it's recommended to put unit tests for something, so these kind of small, tiny tests that are very, very specific. you're recommended to put these into the actual file that contains the implementation. So that's how that works like. I'm creating a submodule that is a module contained in my string library here. I'm making sure that it only gets compiled when we are in test mode. And I'm marking it as test so that it can be picked up by the test runner that comes later. And what these two programmers now do is set up some test data here. So in Go, this looks like that. We have kind of an anonymous struct. Then we create an array of this. Yeah, it takes a long time here to get this Unicode character going. You hardly see it, but it is a Unicode O kind of thing. And in the Rust world, I'm just using a tuple, a list of tuples here, because it seems simpler to me. So Rust does have real tuples. And what I'm doing here now is, I'm kind of accelerating this now if you wonder why I'm typing so fast. What you see here is that I'm destructuring this tuple while iterating the individual tuples just to be able to use them by name. So input and want, and then I can just put this here into a simple assert equal, which is a macro again. So these exclamation marks mean it's a macro. And here we had to do the typical Go thing, right? With if it's not the right thing, then T, error, blah, blah, blah. That's how that works. Let's see here, I did some silly syntax mistake once again. In the Go world, I'm already further and realized that my implementation is actually wrong. In order to fix it, all I have to do is to put byte into rune, and I'm done. And now on the Rust side, I realized that, hey, something is definitely wrong. And here, actually, I finally make the program right, because all this extra stuff that I had to do to force-feed it a character can just now go away. And that's the function in Rust. Much more concise, much more easier to read if you compare it to the respective Go version. If you ask me, really, it's my opinionated comparison here, but that's how it strikes me. And commit and done. Good. Now that we have the testing right, our thing works, we should deal with documentation. It's something that you always have to do, especially with when working in open source, because the world is potentially reading what you write. Make sure you have nice documentation in order to gather a community. Documentation is so important. Maybe you didn't see it. I executed cargo doc there, because cargo doc is the way you use to build docs for your program. In Go, I tried godoc and variations of these, because I thought, okay, probably it is there. In Rust, I'm already trying to figure out how to open or look at these built docs that it put into the target doc folder. This is kind of funny, because I at some point realized how to really do it, but here it's like, okay, how do I build documentation in Go? And honestly, maybe I just don't know better, but I really tried this, and that's the second time I run into this issue, and it's not that easy to me. So I tried to get this godoc tool that I have to pull from this site, and it moved, and some things you find on the internet are not the right ones anymore. And really, until I found this, it took me just a moment. And then I tried to figure out how to use godoc, and yeah, that takes a while. Here in the Rust world, I'm already documenting my stuff. This is a special doc string. So you have normal documentation that is similar to the one in Go, like just 2 slashes. But you have / exclamation mark. Then you write documentation for your crate, which is basically your entire library. And these triple slashes are documentation for the respective item above which you write this. This is how that works. This supports full Markdown, by the way, so it's hard to see here, but these backticks, they will resolve to some Markdown fanciness. So what I just did looks like this. If I built this with cargo doc, I have a nice simple documentation page that has an operational search bar here. Works just fine. This is also the same engine that the official Rust documentation uses. So the Rust standard library uses this to make it work. So you've got the same great tools here. Then, in Go, obviously, this is a bit different, because you just use normal doc strings here. And once you manage to actually run the Go docs server, you realize that it makes, well, that it gives you an entire Golang page with lots of additional stuff on it, but including your documentation that you just produced. It's quite amazing. I was once again surprised that it works that way. Maybe there are offline documentation generators, maybe in the sense of possibly, but it's not part of the standard package that you get when installing Go. And that's quite an interesting thing to note there. Oh yeah, that's me trying to control TTY play, so just ignore this. Now that our program works right, it's documented, we can go to phase 3 of a project, which would be benchmarking, right? If we have so much time left, we want to make this thing fast. And both languages have great support for benchmarking, or decent support for benchmarking. In Rust, this looks pretty much like this. We just go into our test section and mark a function as bench, which is a benchmark, obviously. You can give it some name doesn't matter, and it takes a bencher as first argument, which is quite similar to what we have here in our Go version. Even though the way it's handled is a bit different. So I'm just deciding here to set up a string with a Unicode character in it that I then want to benchmark. And in the Go world, obviously, you're kind of, well, bare bones. Is a loop bare bones compared to the Rust version? It is, because you have to loop through your iterations that have been given by the benchmark instance there. And that's how all that works out then. Here, this part is the initialization part, which is outside of any measurement. Here you can do expensive work. It won't affect your measurements. And within this iter function, we pass a closure that will then execute our actual test. And what I'm saying here is basically, well, execute our reverse function, and the result will be swallowed by the black box so that the compiler doesn't get the idea to optimize that away, which can be a problem. Because optimization, after all, wouldn't be good optimization if it wouldn't be able to do that kind of stuff. In the Rust world, the Go world, pardon, we're already done. We have this 584 nanoseconds per operation measurement for exactly the same string, the same operation. Now in Rust, we managed to achieve the same thing. And let's wait for it. It's 179 nanoseconds for essentially the same thing. Correct me if I'm wrong, but it's kind of the same naive implementation of a Unicode-compatible reverse, which yields us, well, 94 megabyte per second. In fact, 94 characters or 94 Unicode characters per second. So Rust seems to be faster in this very simple case, but whatever. It's not a real benchmark after all, and take it with a grain of salt. Argument parsing is something I just put in for good measure so that you can see some more of the language itself, just because we want to get prepared for the fun part, how to handle dependencies. And for that, I'd like to have a program that I can hand some string that it will then reverse from me and spit out the reversed string on std out. So argument parsing and Go, that's really the straightforward implementation that I think is one of the best ways to do it. Just check if you have enough arguments, and then you basically go ahead and use whatever you get. This looks very different. This looks very different in the Rust world, because apparently we get an iterator here that is containing the arguments and then collect on it. The reason for this is that your arguments, they're not the arguments provided on the command line, they're just bytes. But in Rust, if you have a string, the string is supposed to have valid Unicode. So in theory, these calls here can fail on you if somebody doesn't pass real Unicode on it, but doesn't pass valid Unicode. So this is why you have kind of do this extra thing here. Something I decided to do to make it more interesting, to show off a language feature that will be used a lot if you write Rust, is this match statement here. Match is a bit similar to the switch statement, but in Go, but it's on steroids. It can do a lot. So what we are doing here is we take this input vector and we destructure it into a slice. And then we say, well, the first argument or the first item in the slice we don't care about, which is the name of the program. The second one I would like to take and then reverse it. So this basically handles the I get 2 arguments case. And this wouldn't compile if we leave it like that, because we don't handle all the cases that can be in that switch statement or in that match statement. But that will be coming on in a second. Let's look at the Go version. I think we are done already. I mean, it's simple argument parsing, nothing special here. And what I'm trying to do now basically is to rename it, which I think I just did, so that it's called reverser and that the resulting program will be called reverser. All right? Yes, that's the thing. In Rust, things take longer, especially I take longer in Rust. There's something definitely visible here, because I have to, get used to the syntax and make the right decisions here to make the compiler happy. It's always it's always watching you, which is a good thing. This is why you use Rust in the first place. But yeah, it also kind of reduces your speed. The learning curve is certainly something to pay attention to. So Go is already done, obviously, and here we are still parsing arguments. Trying to. Okay, can at least tell what you see here. We are basically writing to std if something else is being passed. And this OK means that I want to discard all the possible errors that could happen if there actually is no error channel, right? I'm just ignoring this. All this stuff is alpha stuff that I didn't, fix yet. But I'm fixing it now, because I don't want to see this all the time. When Rust goes better, by the way, this will be a non-issue. This is just something you have to do now to make the compiler happy. Good, it builds. So far, so good. I think what's up next is to rename this program here and make sure it's definitely called reverser. I'm just checking on this by having a look at the target folder. It's still called ruler. So what I have to do is basically just to rename it, and I'm done. I would definitely like to speed this up. Maybe I'll just skip it. Maybe we will be done in a moment anyway. So as you can see, the file name is definitely relevant to it when it comes to how to name your program. In this case, it will have sensible defaults, but even within that file, you could specify how the output file should be named when it builds that. So you have lots of possibilities. What you see here is just kind of the default simple stuff that everybody gets out of the box. You have full control over everything in Rust. So there's nothing to worry about. And yeah, sure. There's a new line missing. That's really it. And then I think we are done. We are able to git add, git commit. And now the interesting part: dependencies. Dependencies is kind of a tough topic in Go. Last time I was presenting a program I wrote called Godi here. I think Dimitri tried to compile it and failed to compile it because the dependencies that I pulled in had changed in the meanwhile, and I didn't kind of specify a specific revision because it's not part of what Go get or Go does for you. So here what I'm trying to do is pull in a library that allows me to to measure string symmetry. I want to compare the string that has been given to a string that I decide on, which is hello world, and then I want to just print out some statements that say how close you are to the hidden magic word that I put here. And the string symmetry library, I might have, basically skipped this on the left side. All I had to do is put it as dependency in my cargo TOML into my project manifest, and this also contained a program version. So that makes definitely sure that everybody who tries to build this will get the right version, but there are even more safety nets built in that will assure that in any way. You see the liberal use of match again. This time I think it's the totally right use. So I've been using it to match against literal values in order to write the right thing. So in the moment I give it some word that makes no sense, it's cold. If I'm getting closer to hello world, it's slowly getting there until it hits a bullseye. Hello there, hello, comma, world. Getting warmer, and I think now we are there. Interestingly, I think they have kind of different ways of computing this. But anyway, it's different libraries after all. even though it's supposed to be the same thing, the same algorithm. Good, that is it for Rust. So we have this cargo toml that we manipulated, and the cargo log file that I'm going to look at right now shows you the actual dependencies that I've been using. Sorry, that was very short, but it contained all the dependencies deeply with all the versions that you've pulled in there. So even if you say, well, I don't care about the version of my library that I'm pulling in right now, in the moment you build it, it will pull a particular version and will record that version in the cargo log file. And you have to add your cargo log file to your repository so that the next guy cloning your repository will get the same log file and thus get the exact same version of dependencies. So proper dependency handling is kind of built in. Yeah, while talking about Rust, on the right side, I try to use a third-party tool that is supposed to do the same thing for me. Because GoGet doesn't do it. GoGet just pulls the latest version always. So I have to kind of mark the versions that I want to have. And GoDeps seems to be the recommended tool that comes up first if you look for it from official sources. And really, it's the first time I use it, and I didn't manage to read the docs properly, as I usually don't do the first time. And I thought, okay, this workspace here, it's probably some weirdness that I don't want to have in my repository, but in fact, I do want to have it in my repository. And the next thing you see is me trying to get that workspace folder back, which apparently contains a whole copy of my dependencies. So the whole idea that GoDeps has is a bit different. It has this deps JSON that contains the dependencies, but you're also supposed to check in everything that you are using. It's fine, it's a different way of dealing with this, but you have to know. And it's a third-party tool, so you have to get it in order to get it right. You have to kind of think of it and fix this problem before you go ahead, whereas in Rust, it's already there. You don't have to do anything, you don't have to think about it even, because it's done for you. Yes, deployment. How do we get our code into the world? There are various ways, obviously. In Go, the common way to do it is just to push it onto GitHub or some publicly accessible place. Even if it's not public, you put it somewhere where it can be accessed by HTTPS. There are probably some other rules to this, but that's how it feels to me. So it's there's no real index to this, at least no obvious one. I know there is kind of one, but this is how it feels to me right now. And Cargo or Rust, it works similarly. You don't need a central repository, but it has one. It has one that is called crates.io, and Cargo is communicating with this thing and is able to allow you to package your crates and publish them to crates.io. So even if you don't have a public repository for your library, you can still put the source code onto a publicly accessible central place. So this is something like pip in the Python world. Very similar to this in a way, but much prettier and much easier to handle. That's for sure. All you do is cargo publish. And before that, I put some API token into some configuration file. So that's how it looks like. That's crates.io, and that's the ruler package I just put there. I put the link to my repository, which in that moment isn't there yet because I didn't push it there yet. So I'm adding it right now, kind of, and pushing it there so that would work now. In Go, there is no central index unless you want to call godoc.org a central index, which in fact pulls or checks all the repositories out there on GitHub, at least, that's what I know of, and builds your documentation and makes it available. That's something I forgot to mention when talking about the documentation part. In Go, you probably don't even want to build the documentation yourself because it's built for you by godoc.org. But it is a nice thing to have your own way to build docs, to review them, and well, to package them yourself without having to rely on pushing to your repository. It's a feature I love. I've mentioned this before. I have to say it again. Cross-platform compilation is something I value a lot because it makes things so much easier. I'm developing on a Mac, and that's kind of what I do. I can develop on Linux, but really I don't ever want to touch Windows if I can. So it's really lovely if I can just build for all the platforms without having to worry. So in the Go world, what we do is we use Gox, or I use at least, which is super easy to use. I just go install, and then I run Gox, and yeah. I forgot to do the /... thing, which I always forget. This is also something that I don't like about Go, that it's kind of not having an idea of a project. For him, it's just a loosely structured tree of Go files. That's how it seems. Loosely structured, well, it's a tree of Go files without a notion of a project, really, sometimes. That's how it feels. And as you can see, I just managed to build in parallel for all the platforms that Go supports. There's more to this. First, you have to build a tool chain that is done for you by Gox. It's super awesome. It's gorgeous. I didn't do the toolchain building here because it takes time, but it's really easy to do. In the Rust world, just yet, you are able to specify a target triple, which is kind of difficult to specify because it's like platform plus CPU architecture plus whatever. It's nothing you want to use, and you need to have the toolchain built on your local machine, and nobody is doing this for you, so it's difficult to do at this point. You probably can't do cross-compilation like this right now, unless you really invest some time. So it's nothing to talk about in the Rust world, very unfortunately, but I'm unfortunate, but I think it will happen. It will happen at some point. Well, after all this time, I hope I am within my time limit somehow. The only thing I can say about that, from my experience, Rust really positions itself as a sweet spot that was empty before. Go, I was actually looking into because I wanted a compiled, fast language, similar to C, but without all the hiccups, so that it's garbage collected, that I don't have to care about memory, was a great thing. But I never liked this toolchain of Go, which is still better than C, definitely so. But I don't like it in the whole scheme of things, especially if you compare it to something like Rust. Also, I don't like the look of Go. I don't like that I can't say that things should be read-only, which I'm used to from C, for instance, and which I do a lot just to protect myself from errors. I don't know if I'm the only one who wants to do that, but there are many things that I disliked about Go, but I took it because there was no one else to fill the void. Now Rust comes, and it's just the thing for me. So what I'm trying to do is to use all my time to promote Rust, to just get people to try the beta. Don't try the alpha, because why would you want to waste your time with all these warnings that you get and trying to figure it out? But once it's better on the 31st of March, go give it a shot, because I think it's going to be worth it. It's going to be paying for itself at some point. But, of course, you've seen it. Initially, you will be slower. Go can be learned in just a few days because it's so simple, whereas Rust really gives you a lot of stuff to think about. I mean, look at the generics templates, and there's a whole world unfolding itself when you dig into generics. It's a complex topic, and even Rust can't change the fact that generics, wherever you look at them, are a complex thing sometimes, if you write them yourself at least, and you would probably do that when you write proper Rust code. So Rust is a more complex language. It can do more for you. The compiler is a whole different beast. It's lovely. It talks to you. It really helps you, but it will also be talking to you a lot initially, because you will do a lot of mistakes that would just compile fine in any other language. And you will ask yourself, what the hell does he mean with lifetimes? And really, productivity-wise, initially there will be a bump and it will go down for you. But once you have reached the point where you're confident about it, I think, summary, conclusion, whatever, I just go on talking about this. At some point, I think it's really the language you want to use for the programs that just have to work in the background, for instance, server-side programs, back-end programs, where you want this thing to just run as fast as possible, where you want maintainable, easy-to-read code. Well, what's easy to read, but manageable code that will never break, that will never have serious, memory-related security issues. Also, something to say, data races, for instance, are prevented by the Rust ownership tracking and the borrow checker that Rust comes with. So lots of bugs you can build in concurrent programs you can't do in Rust, at least not without the compiler telling you, so that you have to work around it if you really are inclined to do so. Yeah, I'm not sure if this were my last words. I hope you liked it. I hope you found it informative. My last words would be to encourage you to really try Rust once it comes out as beta. And if not as better, then at least at the 15th of May, when it comes out as first first official release with a stable standard library and lots of packages and a big community ready to go. Community is great in Rust. I like it already, and yeah, thanks for listening. Are there any questions? Oh, sorry.
Using homebrew for installing Go, right?
For installing what?
You install Go using homebrew, is this correct?
Question was, did I use homebrew to install Go? Yes, I did.
Yeah, because I'm asking because I use the tarball the Windows installer, and in both cases the Go command was available, so perhaps it was just homebrew.
See, so I'm stumbling. I'm saying it's my own thing, and yes, apparently, that's what happens if you use homebrew. It's the same thing with Rust, though. By the way, if you install Rust using homebrew, then cargo will be missing, which is a big thing, you know. So this is the thing you kind of realize very early in your development process, whereas Go doc kind of happens to be missing later. Yes. Rust supports C interop both ways. So you can call from C into Rust and from Rust into C. I didn't prepare an example here, but if you go to golang.org, you can check out the C support they have. And C interop is part of their, it's built in, it's very, very close to Rust. And it's very, very fast, so you don't have any kind of crud that is wrapped around it by the compiler or something. What you have to do is similar to Go, to C conversions, that you have to build something around it to call into the unsafe C part of your program. It's very similar to that, if you ask me. I've never done that, though. I've never called from such a language into C, but you can. I think I forgot to repeat the question, but anyway. Yes, please. The question was, how do you support dynamic libraries? In the cargo TOML, you can specify a link type. So the default link type to your library is, I think, rlib, which is the Rust lib, which is like a static library thing. You can also link dynamically. You can say dylib or something, and then it would try to link dynamically to external libraries. So that works, but I've never done it, obviously. But that's what I know from reading the docs. Yes?
One of the pain points we see is Meetup, right? It's the most thing if you talk about security leaks, usually it's some guy forgetting to get the right size and whatever. Yeah. So that's why they introduce garbage collection. What's the answer with Rust for that problem?
Yeah.
No, we don't do garbage collection.
Yeah. So the question was, if malloc kind of is the origin of all memory-related problems and double freeze and whatever, and dangling pointers, if that is the origin of all problems in C, and Go solves this issue with a very good, decent, fast garbage collector, by the way, how does Rust actually solve this problem? Well, Rust solves this problem by ownership tracking. Because the box you have seen there, in the very first example, for instance, it can only be owned by one person. So if you pass this around, ownership gets transferred. It will never be de-allocated by two people at different times, because it will only ever be owned by one person, which will then at some point drop the box, which will de-allocate the memory. And this is how that works. And this will always work, because Rust ownership tracking and the borrow checker, you know, if you borrow your box, then Rust knows about this, and the compiler will assure that double freeze do not happen. You know, they're resource reference counted pointers, they are atomic reference counted pointers, there are all kinds of structures that you can wrap around your heap allocated things to add features to them, to make them usable in different cases or in different applications. This is how Rust does it. It's a complete compile time verification of program sanity when it comes to memory leaks. When it comes to something like double freeze. As I said before, there's no garbage collection, which also means that you can definitely have two strong pointers pointing at each other in some way, and then the stuff will never be freed. So that's something you have to deal with yourself. Yes. Yes, there you go.
What do you think will be the field of application of Rust? How are people going to use it, in your opinion?
Whoa, the question was, that was a difficult one. How do I think is Rust going to be used? What's the main application? What's the main field of Rust usage? Well, I can't, I don't know. I left my ball, well, I can't say that really. I left the glass ball at home, so I can't really make any prognosis, but I think it's used by people who consider themselves unable to deal with the complexity that today's programs will have, especially when concurrency comes into boat. And I'm one of these people. And I want a strong tool that just allows me to write anything without having to worry about a whole bunch of areas that can cause bugs in my program that I will spend a lot of time on finding and fixing, or people will find it and cause me to fix them, which is even worse. And so the main application is basically everywhere. Right now, I see that there's a strong tendency of real-time application or real-time programming applications to use Rust, like games. Rust has OpenGL bindings, has its own game engine already that is in the works, useful for simple games, and that's what they use it for right now. Backends, you have everything already, like database access and such. I think, yeah, we had someone here too. Yeah.
What's with the memory leaks? Are there any checks for that, or you're using Parsing for that?
The question is, if there are memory leaks, are there checks for this at compile time, I suppose, or do you use Valgrind? I think it's pronounced Valgrind. I read it on the wiki, so I really try hard to pronounce it that way. You can use Valgrind with Rust programs too, in order to find memory leaks. So if you have strong pointers pointing to each other, Valgrind will be the tool to tell you about it. So that's the same thing. So a call, I don't know, is it Carlgrind then, callgrind, and Valgrind, they can both be used with Rust programs just fine. GDB, yes. Is GDB supported? Yes, it is supported, just standard stuff. Amazingly, I was surprised myself. You can use GDB. There are scripts online that kind of make it easier for you to get the breakpoints right. I tried to use GDB once and kind of failed, but I didn't find the script that sets GDB up to work with Rust programs, because you want to set breakpoints. And I'm honestly not the GDB command line guy. I need to use user interfaces to do this. And so if you're used to GDB, for you, it will be simple, especially if you're using these repro scripts that help you. Oh, yeah. The answer was actually a statement. I'm just going to repeat it. So possible applications for Rust. Well, the main reason for Rust's inception was that Mozilla wanted to write a new super fast concurrent layout engine that is difficult to do in current programming languages, if you don't use Go for this, I suppose. And even then, it's difficult because of the typical multi-threading issues that you can still have even in Go if you're not careful. So yes, that's what Rust was initially meant to be there for. Servo is this layout engine, is called, and is probably the most massive, biggest project that you can find nowadays written in Rust and being open source. All right, I see no more hands. That shall be fine with me. I'm looking forward to having a cool beer and talking to you guys about Rust and Go and whatever you like. It's also Fasching, Carnival or something, so we can do party sometime later. Okay, thank you very much.